Hey guys. Okay, so we're back. We're talking about introduction to waves. For most of you, this is going to be the first time you've dealt with an information on waves. Okay. So first of all, a wave is a transfer of energy, creating when a moving source creates a vibration. Vibration is just that back and forth motion. It is not transferring matter. It's like I'm hitting my desk. I'm making sound waves. You can hear them. No pieces of my desk flew off. They're still all together because matter is not moving. Mechanical waves require a material through which to travel, or a medium. A slinky is the wave is traveling through this slinky. Sound is going through the molecules in the air. Okay, we can't see it, but if there was no molecules, particles, there'd be no sound. Why? There's no sound in space. There's not a lot of particles. You're not creating the vibration. There's no sound. So that has to have something to go through. It's mechanical. There are two types of mechanical waves. The first is transverse. Okay, the medium is moving perpendicular to the wave. Okay, perpendicular. Talk about this in math class. So when I take a rope and you're swinging the rope, so my hand is going up and down, but the energy is going that way. If I'm moving up and down and energy's flying out like this, okay? Something like that. Three things we need to know about a transverse wave. The highest point is called the crest. The lowest point is called the trough. And a wavelength is from the point in the middle, distance from a point on a wave to the same point on the next wave. Usually measured crest to crest or trough to trough. Amplitude, that's how much energy it has. Okay, so if you have this is the line of rest. Okay, just a line of rest. And in a transverse wave, if it's going up and down, that's low energy. Can you see? Now, if I get something and I'm going like this, that has higher energy. The amplitude is from the line of rest right there, and then I would measure from the line of rest to the crest. That would be my amplitude. Bigger, higher amplitude, more energy. Think about waves in the ocean. If they're bigger, they're carrying more energy into the coastline. Okay. Waves in the ocean are a transverse wave. They're going up and down. If possible, if the ocean could ever stop moving, it would be a line of rest, and then the waves are going above it and below it and above it and below. You don't see the below. So you can see crest, trough, amplitude, line of rest to the crest. Wavelength is from crest to crest or trough to trough. Longitudinal wave is a little bit different. Okay, they're measured from the tightest point of compression to the tightest point of compression. That is one wavelength. We call the compression is where it's the closest together. I would say think about sports. If you ever had to wear compression shorts, they're really tight and they help you. So compression, really close together. Rarefaction, pulling apart. So electromagnetic waves are transverse waves that do not require a medium through which to travel. This is the sun. The sun is giving us electromagnetic waves. They're not traveling through anything. They're going through the empty space. Light's going through empty space. Or vacuum. Light travels at the speed of 3.0 times 10 to the 8th meters per second. You're talking about exponents right now in math class. Think about that number. 10 times 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 10. That's fast. Okay. Examples of the electromagnetic spectrum are going to be radio waves, infrared waves, visible light, and X-rays. We're going to talk more about knowing the whole electromagnetic spectrum as we go on through this unit. Types of mechanical waves. Okay, so now we're on to the second one, longitudinal, the one we just showed with compressions and rarefactions. The medium moves perpendicular. So I'm starting the wave going like this, and the wave is continuing. So it's like that is